Let me say this is joint work with Nicola D'Alesi and Massimo Lauria, and it's a direct continuation of the talk that just was given by Stefan. So I'm in a very fortunate situation now that I can skip lots of the introductory remarks. I have some material anyway prepared, but I think we can go very fast over this just as a quick reminder. So we've seen already in some talks this concept of parameterized complexity. Here you have a few typical problems, like if you're asking in a graph for a vertex cover or for a click of certain size, then the natural parameterization is just the size of these objects. And Stefan told you about weighted CNF satisfiability, where you are asking if there is a satisfying assignment with weight k. Now, all these problems are classically hard. They are NP complete. But if you go into the parameterized framework, then the situation becomes different, and you see a more fine-grained analysis of these problems. Here you have again these complexity classes that were mentioned already several times. And now the picture emerges that vertex cover is in fact fixed parameter tractable, so is efficient in this framework, whereas click is W1 complete, and weighted CNF SAT, as Stefan was pointing out, in fact is complete for W2, so they are probably not efficient in the parameterized framework. And Stefan was also mentioning this, that from the weighted CNF SAT we can come to parameterized contradictions, where we now have formulas in CNF and ask if they don't have satisfying assignments of weight k. Then this leads to a problem which is complete for co-W2, and here's in fact another problem that can be very naturally expressed in this framework. So suppose you have an undirected graph, and you know that this graph doesn't have a vertex cover of size at most k. Then you can build a formula that takes variables pu, so u are the vertices of the formula. And for all edges that you have in the graph, you take up these clause saying that either you must pick u or you must pick v, and then you add k, this parameter, and then this is very naturally a parameterized contradiction, which by the way would not be in ordinary tautology. So Stefan was introducing various kinds to look at proof systems in this framework. And I will just look in the following at the very simple system of tree-like resolution, where we just have this one rule and proofs of in tree-like form. And from a practical point of view, this system is very important as it connects to DPLL algorithms. So all current DPLL algorithms, all SAT solvers, they use extensions of this system. And it's known that on unsatisfiable formulas, they produce tree-like resolution refutations. So for this reason, analyzing tree-like resolution will tell us something about running times or hard
implementation are not tree-like anymore because they use learning.
Yes.
You really mean classic DPLL.
I mean classic DPLL. That's right. And so in this way, analyzing these simple systems will tell us something about performance of these algorithms. And what we would like to do now is to study this in a parameterized framework that was already introduced by Stefan in the previous talk. So let me just remind you, we use tree-like resolution now, so we just have the tree-like resolution rule. We take axioms from the clause set, and we have this, what Stefan called the naive encoding of the parameterization, that we take up all these parameterized axioms. So the proof size is just as usual the number of clauses in the proof, but as Stefan was also saying, we only count the parameterized axioms that we actually need in the refutation. And full refutations, now the full search space becomes of this size, n to the k. And what we want to do is distinguish between short proofs, which are of this format, and full search. What I want to tell you more about now is some proof technique that can show lower bounds in these tree-like systems, also in the parameterized world. And in fact, what I will introduce to you next is a two-player game that yields a general technique to prove size lower bounds in tree-like proof systems. And we kind of illustrated that technique on the pigeonhole principle, the linear ordering principle in tree-like parameterized resolution. And I think as the most important contribution, we analyzed the click formulas in random graphs. So that result was already mentioned by Stefan in the previous talk. And what I want to do now is to show you a bit of the proof and the general technique that is behind this. So let me start by saying something again on these click formulas and what is known about complexity of click in random graphs. And then in the second part of the talk, I will say something about the proof technique, so this prover-delayer game, and will illustrate it also on an example. So here you have again these click formulas. Let me quickly remind you of these. You have a graph, and the formula click gk contains these clauses. So you have variables xiv, and the variable xiv indicates that the ith vertex from the click is the vertex v. So this is a variable which indicates so you number the vertices that you want to put in the click, and the ith vertex from the click is v, yes or no. Then you say that, okay, each index must go to some vertex. You say that, well, it goes to at most one vertex. And now for every non-edge, you say if u, v is not an edge, then you cannot simultaneously pick u and v. So you can pick at most one of these things. So this is obviously a natural formalization of the statement that we do not have a click in the graph. And in fact, as a nice observation, you can see very easily that this formula is in fact invariant with respect to parameterized axioms, meaning that if you have a proof of this formula, or refutation rather, in parameterized resolution, then this will be of the same size as in classical resolution. This is simply for the reason because if you look at the second type of clauses here, every parameterized axiom that you might want to use is actually a weakening of these axioms. Just because you have k indices, and then if you have k plus 1 variables, in these k plus 1 variables you must have two variables with the same index. So the parameterized axioms, they do not add any power to in refuting these formulas. So what we can do is, instead of looking at parameterized resolution, we can as well study the classical complexity in resolution or tree-like resolution of these formulas. And we will do this in the well-known model of random graphs introduced by Erdős and Rainey, where you build random graphs over n nodes, and you choose the edge probability for each edge independently according to some probability p. And now what is known, that if you fix some number k, then there is some threshold probability that depends on this k and on the number of vertices, such that if you go below this threshold, just even a little bit is sufficient, then with very high probability you do not find k clicks in the graph. Whereas if you go with the edge probability over this threshold, then with high probability you find many clicks, many k clicks.
It's just not strictly smaller.
Yes, you're right. Right? Yes, it's an asymptotic formulation. Yes. Thank you. Yes. Okay. So what is known about the parameterized complexity of click? So there is a very important result by Rossmann some years ago that shows that click is hard for constant depth circuits, and more precisely he shows that you need to have AC0 circuits of this size to decide click. More precisely, he shows that every small AC0 circuit cannot distinguish between a graph from this Erdős-Rényi probability distribution and the same random graph, but where you plant the k-click. So in this graph you have a k-click, but in this graph, if you go below the threshold, then you will not have k-clicks with high probability. And with high probability, every AC0 circuit cannot distinguish between these two objects. So of course, what you would ultimately like to do is to extend this lower bound, which is a very strong lower bound, to stronger computational models, so eventually even for Boolean circuits. But as you all know, this is a very complicated task. We do not know any conditional lower bounds for unrestricted circuits. So this next result that Stefan was already mentioning is some kind of orthogonal result, because it looks instead on a family of algorithms, namely DPLL style algorithms, and tells you that, well, this computational problem encoded in the natural way, as I explained before, is hard for parameterized resolution and therefore also for parameterized DPLL procedures. So again, the result says that if you fix these values, k and the probability, then in a random graph, these click formulas require tree-like parameterized resolution, or you can just say ordinary tree-like resolution, because as I told you, there is no difference, of full size, so of n to the omega k, with very high probability. Now what I want to do in the remaining time is to explain you a bit how you can obtain this result. What I will do first is I will first explain to you the prover-delayer game. That is the technique to obtain lower bounds of this format. And then I will also explain how you apply this general technique to the click formulas, but in fact I will not show you the lower bound for random graphs, but look at a simpler graph where the proof is a bit easier to understand. Okay, so let me start by recalling a well-known, I should say classic game for tree-like resolution that was devised by Pavel Putlak and Russell Impagliazzo. This game works as follows. So you have a set of clauses in n variables, x1 to xn, and then you have two players, prover and delayer, and they interact with each other. So the delayer in the beginning is saying, oh, I know a satisfying assignment for this formula. This cannot be so because, I forgot to write down that f should be an unsatisfiable formula. So f is unsatisfiable, and so we know that the delayer certainly makes a false claim. Delayer is saying, I know a satisfying assignment, and now the task of the prover is to, well, catch him in some contradiction. So what he's going to do is he's asking variables. The game proceeds in rounds. Each round starts by prover asking some variable. What is the value of xi? And please tell me about your secret assignment. And what the delayer is doing, he has two choices. So either he can say, well, for xi I have the value 0 or I have the value 1, or he can be even more bold in some sense and say, oh, in fact, not only do I have one satisfying assignment, but I have so many satisfying assignments that, well, you can choose the value yourself. I don't care. And whenever he makes this very bold move, the delayer will get 1 point. So it's clear that the prover will always win the game, because at least if he queries all variables, he will find a contradiction. So the game is over as soon as we falsify one of the clauses from the formula. But the question here is, how many points can the delayer earn during this game? Yeah, prover can always win, but how long can delayer pretend that he has some solution, and how much does he score during that game. And the underlying idea is that good strategies for the delayer for an unsatisfiable CNF in fact yield lower bound for tree-like resolution refutations. Because, and this is so because the following theorem of Pudlak and Impagliazzo tells you that if you start with an unsatisfiable formula in CNF that has a short proof in tree-like resolution, say a proof of size at most S, then delayer will score at most log S points in each prover delayer game played on F. So there is a prover strategy that prevents delayer from earning too many points if the proof is short. So now what you want to use is the contrapositive of this to obtain lower bounds for proof systems. So consequently, if you have a delayer strategy that shows that you score at least P points during any game on F, then you know that, well, resolution proofs in tree-like format must be at least this big. Yeah? So in some sense, it's a very nice way to look at these proofs, because you are transforming the negative task of proving some lower bounds, so some impossibility result, into some positive task that you come up with some delayer strategy. And well, now if we want to use this proof method in parameterized resolution, we encounter one problem, namely the proof trees in parameterized resolution are always very unbalanced. Because you can at most set k ones or k plus 1 ones, and then you will immediately falsify a parameterized axiom. So then there is a simple prover strategy. Always, if he gets the choice, he will answer 1, and the layer can only earn k plus 1 points in this way, and we will only prove this lower bound, which is trivial. So we must do something better, and our idea was that we modify this to something we call an asymmetric prover delayer game, where we assign points asymmetric and according to some kind of information that prover is revealing by making his choice. So the game proceeds as before, but the delayer will get different points when the prover answers 0 and answers 1. More precisely, the score will depend on two functions, C0 and C1, that depend on the variable that is queried and also the previous game history, so the partial assignment alpha we've constructed, such that we meet this equation. And then, as before, if the layer chooses the value herself, then we don't get any points. But if prover sets the value to x to 0, then we get log C0, and if we set the value to 1, then we get log C1 points. So you can see the previous game is some special case where these functions are constantly equal to 2. Yeah? Then you always get 1 point for both answers. Now, the idea is that these functions C0 and C1 should relate to the amount of information that prover provides for his 0-1 choice. And you will see maybe in a minute that you can also interpret this as saying that the layer scores according to some fraction of the proof that is avoided by prover. Now the combination or the relation to proof sizes is given as an analogous result as the one that I showed you before of Pudlak and Impagliazzo. So again, if you have a parameterized contradiction and two functions meeting this requirement, and you have a short proof of some parameterized contradiction, so short proof means you have some upper bound S, then again the layer will get at most log n points for each C0, C1 game played on Fk. And well, let me just make a very small remark on the proof. I think time is not really permitting me to show you all of it. So suppose you have a parameterized contradiction in these variables, and if we choose a parameterized resolution refutation that we know exists of this size S. So we interpret it as a Boolean decision tree, And now the strategy for the prover is he queries variables x labeling the root of t, and then whatever decision is made in the game for x, prover moves to the root of the corresponding subtree and queries the variables which labels that. And so this induces a root to leaf walk on t. So during the game we will move in the tree from the root to some leaf. And now the important point is the clever prover, what kind of strategy he should use. So if he has to answer to variable x, then he answers probabilistically and exactly with these two probabilities. So you see, first thing is prover strategy is randomized, and let's denote for delayer d by PDL the probability of the game to end at leaf L. Now we make the following claim. If the game ends at some leaf L, then the delayer will score exactly log of 1 over PDL points. So yeah, you have again the claim. So the claim implies the theorem. Maybe I can show you this and then the claim I will not prove. So let PD be the distribution on the leaves. So this game induces some distribution on the leaves. So then what is the expected score of the delayer, because the prover is randomized? Well, you go to this leaf L with probability PDL, and by the claim on this process going to this leaf, you will score log over 1 PDL points. So then the expected score is just the sum, which is exactly the entropy of this distribution, the entropy of the distribution on the leaves. Now you know that, well, there are at most S leaves, and you also know that the uniform distribution has maximal entropy, so therefore you get this bound. And now you can just fix the random choices of the prover, and then you get the statement. Okay, so maybe I skip this, how you prove this claim, because I want to make some illustration how you use the technique to actually prove lower bounds. I will not do it for the random graphs, but will consider a simpler case of a k-1 partite graph. So here you have k-1 blocks of n vertices each, and you have all edges between blocks as indicated here, but inside the edges, inside the blocks, you do not have any edges. So certainly this is a graph that doesn't have a k-click, and we want to analyze the complexity of the click formulas on these graph classes. So in the light of the connection to the prover delayer game, what we have to do is to find a delayer strategy that scores many points. How does it work? Here you have the delayer strategy. You query variables x, I, v. So you want to know is the ith vertex of the click vertex v. And then what you should do as delayer is first answer consistently. So what does that mean? Suppose the partial configuration that you have in the game is this click. So you have chosen these three vertices. And now suppose that you ask this green vertex here. Then what the delayer should do is of course say no, because otherwise you should exclude this vertex, because otherwise you will immediately get a contradiction because there's no edge here. Now consider another example that you ask this node here, which in fact from this block is the only vertex that is not excluded. So you have excluded all the blue vertices and you're asking now this one. Then it would be a bit stupid for the delayer not to answer 1, because otherwise he will lose this block completely. So in this case he should enlarge the click and include this vertex. But in all other cases, and in fact this will be the majority of cases, you let the prover decide and score some points. Now, what I would like to show is, and maybe I can show you a bit of this in the remaining minutes, that in fact what we score is should be this number k-1 times log n points. So in fact you should, on each of the blocks, you should score log n points, and that will give a lower bound of this form. Okay. Now some details on the delayer strategy. So let's denote by Zj the excluded vertices in block Vj. and we are asking about vertex Vj. I told you already we answer consistently, and if V is the last vertex, meaning that this cardinality goes up to n-1, we answer 1, otherwise prover makes the choice. Now the score function is this. If the prover makes the choice and answers 1, then we get log of Vj minus Cj points. So this number will be exactly the number of free vertices. So the Zj are the numbers are the vertices that are excluded from block J, and in total there are Vj, which is n. So it's n minus so it's the number of free vertices that are still there. And if you want to fix a vertex in block J, then this is exactly the information. So you need log of the number of free positions, log of these bits, to specify exactly where the which vertex you put into the click. And if you put the 1 there, then you get exactly this number of points, which corresponds to the amount of information that is still undecided. And for answer 0, you get this bound, which you can just calculate. Now, let me comment again on this intuition that we have for this. The delayer should score points according to the revealed information. And this means then that when prover selects a vertex from block J, the delayer should always get about log n points on that block. That's what we want, because that's really the uncertainty. If we have one block, then we need log n bits to specify which vertex we want to choose from that block. So in the end, he should get log n points. And when we play the game, then in each round, the delayer should get some number of points that are proportional to the progress that prover makes towards fixing the vertex from block J. Let's look at some examples that illustrate that better. So suppose that prover selects vertex V from block J in the very beginning. So nothing is known about block J. And at the first query, the prover says, I put a 1 there. Then the delayer should get the log n points immediately. And in fact, that's what he does, because this is 0 and this is n, so he gets log n points. And the second example, suppose that we have excluded n-2 vertices already, then it doesn't matter whether prover sets the thing to 0 or 1, because after both answers, you know what is the vertex. So either you choose this vertex or the other one. And in both cases, you can see that he gets 1 point, because I mean this is n-2, so log of 2 is 1, and here is also 1. So now, how many points does delayer score in total? So from the delayer strategy, you can quite easily verify this claim that at the end of the game, you have chosen a vertex in each block, because delayer is playing consistently. And now, how many points you get per block? You can calculate this independently. There are two cases. Namely, either the vertex was chosen by the delayer or the vertex was chosen by the prover. And in case 1, if delayer sets the 1 in block J, then you know delayer is doing this only in the very end, if he's forced to do that. So he scores lots of points for all the zeros, and all the zeros were put by the prover. So in fact, he scores this number of points, and then you see just this gives log n. Yeah? And in the second case, if the 1 is set by the prover, okay, this can happen at any time in the game. So let's say it happens after some number r of vertices are excluded. So there are a number of zeros already in that block, and let's say r is that number. So if prover sets the 1, then you get, well, the points for that prover decision. So these are the points for the 1. But also you don't have to forget that you get some points for the zeros. And this is exactly this number. And if you make the calculation again, you see it is always log n. So for each block you get log n points. And so in total we get this many points, and as a corollary we can say any tree-like parameterized resolution refutation of the click formulas on complete k-1 partite graph must have this size. So, in fact, a similar but somewhat more complicated strategy is also working for click formulas for random graphs. and also works for pigeonhole principle and linear ordering principle. And I was saying it's a general technique, so in fact you can also use the technique to give a quite elegant proof of the optimal n factorial or 2 to the n log n lower bound for the pigeonhole principle in classical tree-like resolution. So let me just conclude. One observation or one statement we can make that is also apparent from Stefan's talk is that lower bounds in parameterized resolution or in parameterized proof complexity are harder to obtain. This is in fact also underlined by a result that we obtained with Alexander Rasborov, that many classically hard problems are easy for tree-like parameterized resolution. And what I've showed you here is a combinatorial characterization of tree-like parameterized resolution by this two-player game, which gives a general technique to prove size lower bounds in tree-like systems. And well, I've showed you how to use this for click, but it also works in a wider context. Thank you very much.
Thank you very much. Are there some questions or comments, please?
Just continuing the conversation we had earlier, there is a tight connection between bounded widths refutations and a particular two-player game using bounded number of pebbles. So I'm just stuck with the analogy.
Yeah, so maybe one remark that I can make. So this line here, which says many classically hard problems are easy for tree-like parameterized resolution, refers to some result that we have that each bounded width formula has a short refutation, so has FPT size proofs. But as we were just checking after your question, our refutation in fact will produce long clauses in the proof. So the proof itself will be short, but you are using long clauses, even though the initial clauses are very small. So, but definitely it's a very interesting question to understand this.
So isn't it like relation between sequence-like and tree-like? That you can simulate a sequence-like proof by increasing the depth by 1 to get a tree-like. So if you simulate width k resolution proof, you get RK tree-like proof, and vice versa. I mean, vice versa might increase k by k plus 1 or something like that, but it should be the same. Or is this not true? Or?
So there's a trade-off between width and depth.
Yeah, I mean, think about the, say, resolution as, or rather about clauses of, or let me say it like this. If you have a resolution where every clause have a width k, then you can, and it's not in a tree-like form, you can create it, put it into tree-like form by proving statements saying if all clauses up to now are true, then the next clause is true. And if you write this as a KDNF, it will be this junction of conjunctions of size k with natural rules, to progress. But you can also reverse this. If you have a tree-like proof like this, then there is a way how to remove the top disjunction and make it just operating with clauses, but it will lose the tree-like property. So I think that this should be true. After all,
it feels like there is a connection here between these two ways of parameterizing the problem.
So are there some more questions or comments? So let's thank the speaker again.